Welcome to this lecture in the ongoing series of lectures in real analysis. Today we are starting a new module. We'll define today the notion of continuity. In a sense, all of the work that we've done so far is basically in preparation for what comes next, and continuity, the notion of continuity is a fundamental notion, well, in all mathematics, but certainly as far as our course is concerned. So far what we have done is we have defined real numbers, and then we discussed some few facts about sequences and convergence, and then we concentrated on special subsets of R like open sets, closed sets, compact sets. And let me not recall any formal definitions. I'll assume that so far we have done the work we have done has made us familiar enough with these things that now we have internalized them, having solved so many problems. So now let me just immediately dive into what we want to achieve in this lecture. So what we want to do is we want to define the notion of continuity formally. And let's say in the simplest case, we would like to at least define continuity of a function which has the entire real line in its domain, and the target could be any real number. So for such a function, we would like to say that it is continuous if sufficiently nearby points in the domain map to nearby points in the target. So note that the adjective sufficiently is only for this and not for this, and we'll see what that means. We'll make this formal. So, well, before even we give a definition, let us try to see what kind of functions we would like our definition to pass as continuous functions and what kind of functions we do not want to pass as continuous functions in the formal sense. So certainly whatever be the definition of continuity, this function better be continuous. So what do I mean by this function? Basically I've drawn the graph of a function. Function is from R to R, but if you draw the graph, it's a subset of R2, and basically this white thing is the graph of the function. At this real number it takes this value. So, and this is basically, you could think of this as a graph of x going to x square, that function. So this better be continuous under whatever definition of continuity that we want to give. Similarly, even this should be continuous. This is the graph of the absolute value function, x going to the absolute value of x, that function. The graph looks like this. And this kind of function shouldn't pass as a continuous function. There's a lot of jumps. So this is basically the greatest integer function that should be familiar from high school. If you take any real number x, what you return is the greatest integer that is at most x. So on 0 you get 0, and if you take, let's say, something like half, what is the greatest integer which is at most half? It is 0. And as you reach this point which is 1, suddenly you reach here because the greatest integer which is at most 1 is equal to 1. So entirety of this you are equal to 0, 0, 0, but then suddenly it's a 1. So this sudden jump violates continuity intuitively, and we need to give a definition which takes care of this. So with that, let me now get to the formal definition. But so even before we get to the formal definition, we need to give some more definitions based on which we can give a formal definition. So first, what is R2? We've seen what this means. This is the set of real numbers. When we write R2, we mean all pairs of real numbers. So R2 is nothing but the Cartesian plane, and we draw it like this. We just draw two lines like this, and at any point here gives you basically two numbers. If you project in this horizontal line, then you get a real number. You project on the vertical line, you get a real number, and every point basically encodes those two real numbers. This ordered pair, x comma y, means this distance is x and that distance is y. So I'm sure this is familiar. We have been drawing graphs in high school, so maybe this notation was not familiar. I don't remember if this used to be discussed in high school, but certainly the notion is familiar. Okay, and now let me define one more concept. So let a comma b be a point in R2. Then the epsilon band. So yeah, so let epsilon greater than 0. So with those two things, the epsilon band about a comma b is defined as something which I will explain via picture, but let me first write it down. So it is defined as the set of all those points in R2 such that x is just some arbitrary real number, but y satisfies this bound. So what are we trying to capture? That we can see via an image. So this image is basically what I want to discuss. So we have this point a comma b, and now suppose x and y are real numbers such that this condition is satisfied. But then x could be anywhere here, because x is allowed to be any arbitrary real number, but y should be between these two. It should be in this interval. So if this is b, what are the so let's say, okay, so you project it here, you get b, and what are the y's which satisfy this? Those are precisely where you're allowed to go epsilon up and you're allowed to go epsilon down, but no further. So these are all the y's, and since x is unconstrained, basically this whole region is the epsilon band around about a comma b. And this is not a standard terminology or anything. I just invented it for the purpose of this lecture. So very simple definition, epsilon band. And I need to also define what is meant by a graph. Now we all know what is meant by a graph of a function, but let me still give a formal definition. So let S be a subset of R. Could be any arbitrary subset, doesn't have to be an interval, doesn't have to be infinite, could be quite messed up. And let suppose we have a function. So let f s to r be a function. Yeah, so the only condition I want to nest is that it is non-empty, because otherwise I won't be able to define a function. S is non-empty. Okay, so the graph of f is defined as, so the notation for the graph is gamma f, and it is a subset of R2, consists of all the points in R2 where x is allowed to vary in the domain of f. So this is exactly what we draw when we draw a graph. So for instance, suppose we had x going to x square, then we pick a real number x from the domain of the function. The domain of the function in this case is the entire real line, and we just track where is fx. Fx is at the distance x square. This is x and that is x square, and we just plot all those points. And what we get is what we call the graph, and that is precisely the subset. So just formalizing what we already intuitively have in our mind. So yeah, so this is our function, and the graph looks like this. That's exactly what I just said. So graph is actually a subset of the plane. I mean, formally it's a subset of the plane. Plane meaning R2. Okay. And one more definition. So suppose we have a function from a set x to a set y, nothing to do with real numbers, just some function from x to y. X and y are sets, and a is a subset of x. Then we define the restriction of f to a as a function whose domain is a, whose target remains the target of f. And what does it do? It consumes something in a and spits out what f did on that number, or not number, but whatever that something is. So what is happening is, one way to say it is, we have this x to y, this function, and a is here. A is a subset of x. So what is this map? This map takes little a to a. Seems silly, but it's a legitimate map. And all we are saying is that this composition is f restricted to a. So we had f, we have this inclusion map. If you compose, then what you get is a function on a, genuinely, this arrow, and it's just a notation that we write it this way. So it seems like a silly thing to define, but it's good to define it because it helps communicate ideas. It's a very simple definition. Okay, so now we will finally define what we mean by continuity. And there are many ways to define continuity, and we'll look at 4 ways in this entire module. The first lecture in this module about what I call the geometric definition of continuity. Again, this is not the way it is enunciated in textbooks or anything, but I think in any lecture this is the way it is conveyed. And I think this is really the essence of continuity. So let f s to r be a function where S is a subset of R. So again, there is no hypothesis on S except for that it is non-empty, which I won't write. And whatever definition we are going to give, the best way to understand the definition is to think of S as a nice set, like an interval, or better yet, just the entire real numbers. But the definition is very general. It applies to any arbitrary subset. It will make sense intuitively only for nice subsets, because we can't really, very well imagine messed up subsets of real numbers. Okay, so we have such a function, and let x0 be a point in S. So then we say f is continuous at this given point. Let me highlight that, continuous at x0. If something happens, and that something needs to be explained properly. So let me write it and then explain it. So if for all epsilon greater than 0, there is some delta greater than 0, such that the graph of f restricted to this interval, and well, we can only restrict to a subset of S, so we intersect it with S, is contained in the epsilon band about x0, fx0. So completely meaningless looking definition, and my basically agenda in this lecture is to convey that this is actually a very meaningful definition. Okay, so what I want to justify is the philosophy of nearby points go to nearby points. Sufficiently nearby points go to nearby points. That is what I want to justify. Okay. So suppose what we have is a point x0, which is here. So let me darken it. This is x0. And this is the point in the graph of f corresponding to x0. So just think of S as the entire real line for simplicity, because that is what affords understanding. Okay. And now what we have done is we have chosen a notion of nearness in the target. We have chosen what it means to say 2 points are closed in R, in the target. So that is what this epsilon is. So some adversary, let's say, has chosen an epsilon that's up to him how big or how small he wants to choose. The only constraint that it should be greater than 0. And then once that epsilon is chosen, what the continuity of the function at x0 is saying is that if we hover close to x0 in the domain, sufficiently close to x0 in the domain, then the image of all those points in the domain remains within that chosen notion of closeness in the target. So if you're sufficiently close to x0 in the domain, you will be close to fx0 in the target. That is exactly what I'm trying to say. There's sufficiently nearby points, go to nearby points. And this is one way to express it. So if you really try to decode it, what this is saying is that the graph of the function restricted to this part is within the epsilon band, meaning is within this, is lying in this region, and where I hope you get that this is epsilon and that is epsilon. Okay, so that's what the epsilon band is. Basically, this dotted line passes through x0, fx0. Okay, so what does this say? It says that if I draw the graph of the function, it will be within this epsilon band. Draw the graph of the function restricted to this thing will be within this epsilon band, meaning the function would look something like this. So beyond this interval, I don't know what happens to the graph. The graph may just behave some weirdly. But at least within this small enough interval, the graph at least well behaves up to epsilon. So that's what this is trying to say pictorially. But what this also, from the graph you can just immediately read that on any point in this interval, the value of the function doesn't deviate by at most epsilon, or rather deviates by at most epsilon from fx0. Because if you let's say choose this point, you get this value, and this value let's call this x. So then this point is x comma fx. But what that means is that fx minus fx0 is at most epsilon, because that is what the difference between the two y coordinates is, and the difference between two y coordinates cannot be greater than epsilon. Both of them are sandwiched between this epsilon band. So sufficiently nearby points in the domain go to nearby points in the target. Alright, so think about this definition. It may not be immediately clear what's happening, but I hope at least it should give you some sense as to that, yes, this is actually capturing our intuitive notion of continuity. The function is not allowed to jump very quickly under this constraint. So this is our geometric definition of continuity. That for all epsilon greater than 0, if somebody chooses even a more stringent notion of closeness in the target, then there will exist a delta, but delta may be further smaller. If you choose epsilon to be 1 upon 10 to the power 10, then this epsilon band is very, very small. So then of course this delta might not work, because the function is, looking like this, at least in this picture. So then you may need to choose a smaller delta, but the point is that if no matter how small the epsilon you choose, there is always a delta, then the function is actually not jumping around that point. So this is a formalization of our intuition, and I would say it's really a very clever formalization. It's not immediate. If you would try to come up with your own definition of continuity, well, once you've seen this, I guess, and once you've internalized this would become very, very natural. But it took many, many years for mathematicians to come up with such a formal definition. Alright, so much, I guess saying too much also obscures understanding. So I would encourage you to think for yourself on this definition, as long as it takes. Alright, and let me then define one more thing. So we say that f is continuous if f is continuous at all points, continuous at x naught for all x naught in S. So here we define continuity at a point, and now we are defining continuity of a function. When we say the function is continuous, what we are saying is that it is continuous at every point in its domain. So as simple as that. Okay, and let me take some basic examples. So the constant function, so let S be a subset of R. The constant function, okay, so let C be any real number, then the function which takes little s to C for all s is continuous. So basically what I'm trying to say is that constant functions are continuous. And again, this is actually very, very clear from this whole business. So what will happen is that, let me copy this image, or let me just argue in this image itself. So here what will happen is, somebody has given an epsilon, so you make this epsilon band. And now what you want to do is you want to show that there is a delta such that the graph of the function within that interval does not escape the epsilon band. But what does the graph of the function look like? The graph of the function is just this horizontal thing. Well, of course, you have to, when you draw the graph, you can only draw the points which are above S. So in this, when I'm talking in this picture, let's assume that S equals R for understanding. So the graph of the function looks like this. Let's say this is C, this point, and this is the graph of the function. Precisely this horizontal line. So whenever you choose a point x naught in the domain of the function, you get this point x naught comma f of x naught, which is nothing but x naught comma C, because that's the only value the function takes. And now if you make an epsilon band around that point, well, of course, the graph of the function doesn't leave the epsilon band within this small interval, because it doesn't leave the epsilon band in this entire real line. So it is as continuous as something can get. So that's fine. And let me also take another example, which is a little bit more interesting. Is that the function which takes x to x for all x is continuous. So meaning it is continuous at every point. Alright, so let us again argue in this diagram. And again, I would encourage you to first argue for yourself and then only look at what I'm saying. Alright, so let me erase these. Okay. We have this function. And let me erase this epsilon band. Okay. So we are given a point x naught, and we want to show that the function is continuous at this point x naught. Let me also erase the blue thing if I can, hopefully. Yeah, I can. So again, we have been given the point x naught. We have this graph of the function has been drawn. The graph of this function looks like this, where this is a 45-degree angle. And we want to show that the function is continuous here. Alright, so what is the point x0 comma fx0? We just draw a vertical line. Okay, so we have located x0 comma fx0, which of course we know is nothing but x0 comma x0 because the function is defined that way. Okay, now we have some epsilon band. Oops, sorry. So we have some epsilon band about this point. It's not very faithful to the... Yeah, okay. I hope this will do. Or maybe this is not even parallel. Yeah. Okay, so we have an epsilon band. We have chosen an epsilon and drawn the epsilon band. Alright. And we want to show that there is some interval about x0 such that the graph of the function above this interval remains trapped in this epsilon band. But there is a very natural candidate for such an interval. It's basically where these intersections happen. You come down and take that interval. So what is this point? This point is just, if you think about it, this descends by epsilon, so this also goes by epsilon because of 45 degrees. So this projected point is, if you come down this way, it's x0 minus epsilon. If you come down that way, it's x0 plus epsilon. So in the entirety of this open interval, the graph of the function remains trapped inside this epsilon band because the graph is precisely this white thing that you see. So therefore this function is continuous. We picked an arbitrary epsilon and showed that actually delta equals epsilon works. Delta here actually is, one can take that equal to epsilon. One could also have taken it equal to epsilon by 2 because if the graph above this interval is contained in the epsilon band, the graph above any smaller interval would also be contained in the epsilon band. So it's not like we have only one choice of delta, we have a million choices of delta. So that's that. The only way to understand this is actually to think for yourself, but I hope things are clear. And now let us see a counterexample. So we do not want this step function, meaning this function, to be continuous. And let's see, does it actually qualify the definition of continuity that we have given? Okay, so I would like to show that the function is actually not continuous at this point. And intuitively here it is where it takes a jump, so it shouldn't be continuous here. So let us argue using our definition. Okay, so I've chosen epsilon to be equal to 1/2. So this is a half and that is a half. And made this epsilon band. Epsilon equals half and we have made this epsilon band. Now, no matter what delta you choose and make an interval around x0 of that length delta, the graph of the function above this interval will always consume some part from this guy. So it will contain some part from this guy, and hence this part cannot be contained in this epsilon band. It's because this part is on the x-axis while the epsilon band is above the x-axis. So there is no delta for which the graph above the interval of length delta around x0 is contained in this epsilon band. So this function is discontinuous at x0. In fact, a very big epsilon shows you that it is discontinuous. So that's an example of a discontinuous function. And again, our definition actually takes care of it. Our intuition is not at odds with the definition. So let me give 2 more examples. And I would also like to highlight a certain subtlety that's there in the definition. So suppose I consider this function f r to r, which is defined as f equals characteristic function of q. So what does that mean? So this function, let me expand on what this means. This means that f of x equals 1 if x in Q, x in Q and 0 otherwise. So that is what is meant by the characteristic function of Q. So it basically detects which points are in Q and which are not. Now, if you kind of try to draw the graph of the function, of course you can't draw the graph of such a function. It's just too wild. But intuitively it should be clear that it is really jumping too much. It's much more discontinuous than what we just saw. It is jumping too much. So argue that this is not continuous at any point. Then f is discontinuous or f is not continuous at any point. Or rather, let me not confuse, then f is continuous at no point. That's more precise. It is discontinuous everywhere. Here, what was the case? We showed that the function was discontinuous here, but a simple exercise will show you that it is continuous in fact here. The only points on the real line where this function is discontinuous are the integers. Everywhere else it is continuous. So it is not as bad as this guy. This is discontinuous everywhere. And I would like you to really think about this and prove this formally using the definition that we gave. So this I leave as an exercise. However, what I want to highlight is that the function which takes x to 1 for all x is continuous everywhere. It's after all a constant function. Constant functions are continuous everywhere. There is no issue about that. So what I'm trying to say is that the domain matters. The function kind of looks the same. It's sort of like the same function, but well, it's not, because the domain is different. So this is an important point. The behavior of the function, a function is not just, in high school we say function is a rule and this, that, but a function is actually three things. It's domain, target, and the way to go, and a way to go from the domain to the target. So the definition of continuity is sensitive to the domain of the function. Here, when we defined the notion of continuity, we intersected with the domain. Because anyway, otherwise it doesn't even make any sense if you don't intersect with the domain here. So please make sure that you get both of these examples. It's very important. Okay, so I guess this is good enough material for one lecture. Next time we'll look at the epsilon delta definition of continuity, which is, I guess, more standard, and that is how it is introduced first. But really the idea is in the picture, so that's why I would start with the geometric definition, even though perhaps this is not in any standard textbook. And we'll see that the epsilon delta and this definition are actually tautologically the same. There is no difference. But I will spend one lecture on the epsilon delta definition. Alright, enough of that. As usual, like, comment, share, subscribe. Thank you for listening, and I'll see you next time.